Have you ever looked up at the night sky and wondered if your heart carries the memory of the stars? We are made of stardust. A gentle story of the origins of life will lull you through a journey, from nuclei igniting in supernova explosions, to the calcium in your bones, the iron in your blood, and the breath you just took. In 15 minutes, we won't argue. We'll simply listen as the universe speaks through the rhythm of light and the ancient history etched into every element. This video promises a sense of peace, understanding, and a fresh perspective on why those distant stars feel so intimately connected to our everyday lives. And if you find yourself smiling before you sleep, hit subscribe to support the Smart Sleep channel. My dear friend, tonight I'd like to invite you on a journey very far away, farther than any interstate, farther than any coastline, past all the mountain ranges that have watched over many generations of Americans, back to the very first moment when darkness itself was still young. After the opening blast of the Big Bang, about 13.8 billion years ago, the universe slipped into a long, lightless night, with only hydrogen and helium drifting in silence, like notes without a melody. Time flows very slowly on the scale of the cosmos. And there, gravity, the most patient of all forces, quietly gathered those wisps of gas, thin as breath, into clouds growing denser and denser, like an old craftsman steadily winding thread. Once the density was high enough, the heart of the cloud heated, brightened, then ignited. The first stars were born. They were huge, fierce, and short-lived, only a few million years. A blink of an eye compared to a galaxy's lifetime. And precisely because they lived fast, they achieved something extraordinary. Using hydrogen as fuel, they forged carbon, oxygen, neon, silicon, then pressed all the way to iron in their cores. Can you hear that very distant whisper? It's the sound of nuclear reactions, as gentle as a fireplace crackling in a Minnesota winter night, yet so immense in energy that they light up vast stretches of space. But iron is a hard boundary. At that point, the game ends. The star can no longer gain energy by fusing heavier nuclei. Its heart collapses so quickly, even light doesn't have time to give a warning. And then, a supernova, not just an ending, but a door being ripped open. In that instant, layers rich in carbon, oxygen, silicon, and iron are torn apart, flung into the cold of space like handfuls of seeds. At the edges of that fiery storm, where neutron density surges and winds of neutrinos whistle through like invisible calls, some elements heavier than iron, gold, platinum, iodine are rapidly woven by frantic neutron capture. In other moments, such elements are born when two neutron stars merge in a final dance, flaring out in a glow we call a kilonova. But most of what's familiar inside us, the carbon in your hair, the oxygen in your breath, the calcium in your bones, the iron in your blood, was forged in stellar furnaces and their explosive last breaths. When the flames go quiet, stardust departs. It doesn't rain down at once onto the prairies of Kansas or the shores of Maine. It drifts through space like a migrating flock, for millions, sometimes hundreds of millions of years, slowly cooling, condensing into tiny grains of graphite, delicate silicate particles, wrapped in icy coats of water, methanol, ammonia, a miniature archive of mysteries, bathed in ultraviolet starlight and carved by cosmic rays. Those grains become stages for prebiotic chemistry. Simple molecules start pairing up, forming longer, more intricate chains, like scattered notes slowly turning into a refrain. Few people ever tell us that dust, the same nuisance that makes us wipe our bookshelves each week, is also the warm blanket that lets gas clouds cool enough for gravity to keep squeezing, birthing new generations of stars. Without dust, gas stays too hot to collapse. Without dust, light would stab straight through, shattering the calm needed for the first seeds of life's chemistry to take hold. It's a gentle paradox. The tiny saves the immense, and then, at the outer arm of a young spiral galaxy, a modest star lights its lamp, the Sunday. Around it, a disk of gas and dust swirls like a spinning record, clumping into pebbles, then planetesimals, then planets. Water likely arrived via water-rich asteroids or icy comets, falling as slow rain over hundreds of millions of years, filling the blue basins. On the young Earth, ancient stardust, some grains still preserving pre-solar signatures that scientists would one day find inside meteorites like those fallen at Murchison mixed with lava, lightning, ultraviolet light, and the breath of hydrothermal vents on the ocean floor. The universe, it seems, was quietly trying millions of recipes, like a patient chef, until one mixture managed to keep a flame alive, a molecule that could copy itself. From there, the rest was time and transformation. If you place your hand on your chest and feel a heartbeat, you are sensing a faint echo of those long-gone stellar forges. Every red blood cell carries iron atoms that once sat inside the core of an alien sun. Every breath brings in oxygen atoms that were flung into space by an explosion more than 10 billion years ago. Every smile reveals calcium in your teeth, bricks gathered by aging stars and passed on through the long night. Those atoms are so durable that their memory is the memory of the universe itself. They don't know borders, they don't know our languages, they only know collisions and bonds. And yet, arranged side by side, in a configuration both accidental and exacting, they suddenly can sing, think, and love. We call that miracle, life. Sometimes, in sleepless nights, we ask, why did the universe choose to create life? Perhaps it didn't choose. That word belongs to human hearts. The universe simply followed a few very simple rules. Gravity, expansion, and constants etched into nature. But the combination of these simple rules, stretched across billions of years, created rare pockets where energy is gentle, water is liquid, molecules are stable enough for a small chain to begin copying itself, and to resist dissolving into nothing. In one sense, life is matter's answer to the chance to delay the final equilibrium. In another, it is the ancestral memory of stars, an attempt to keep the hearth fire burning longer, this time within living warmth. There is one detail rarely mentioned, and I'd like you to ponder it slowly. When a massive star explodes, most of the energy doesn't leave as the brilliant light that dazzles our telescopes, but as neutrinos, ghostly particles slipping through Earth as easily as a breeze through curtains, roughly 2/3 of a second after the core collapses. A storm of neutrinos blows the star's material outward, keeping the blast from failing. If that invisible breath were a little weaker, the heavy element-rich layers might not escape. Dust might never form, and our story could have ended before it began. Each night, trillions of neutrinos pass through your body unnoticed. Perhaps a few are distant cousins of the gust that first enabled the sowing season of elements. Here's another secret. Lithium, beryllium, boron, the three rare elements that appear only sparingly in our bodies, are not easily made in stellar cores. They're carved out when cosmic rays, protons and nuclei, accelerated by supernovae, smash into heavier atoms in space, shattering them. So besides blazing furnaces, the universe also uses cold chisels, sculpting subtle fragments, If you've ever seen the night sky from an Arizona desert, far from city lights, you know how vast and quiet the universe can feel. In that stillness, a workshop is working around the clock. Each speck of stardust is a diligent worker, carrying chemistry onward. Each shock wave from an explosion is a drumbeat, urging clouds to collapse. Each line of magnetic field gathers dust into threads, giving the first droplets of water a place to cling in the cold gas. The smallest things uphold the grandest. When you hear "we are made of stardust," please don't treat it as a poetic metaphor. It is as concrete as a graphite mark on white paper, as real as the salt taste of sweat on your forehead. In laboratories, scientists find pre-solar grains trapped inside meteorites that landed in farm fields in Australia or the Sahara. Isotope analysis reveals the signatures of stars that died long before our sun ever rose. Those grains traveled distances beyond imagination, and some tiny fraction of them, by a winding path, became part of us. Realizing this, we soften a bit. We're not out of place. We're the next chapter of a very long story. And if one day life feels cramped, remember, inside you is a record of eruptions and repairs, of scattering and gathering, of burning bright and cooling at the right time. You are proof of a fragile balance between chaos and order. You are where the universe tested its patience and succeeded. But the question remains, whispering like a lullaby. Why, in one small corner of space, did Stardust choose to become beings who dream? Perhaps the answer is not a single equation, but a very human feeling. The sense of meaning. When we ask that question, we reconnect the first night of the universe with tonight's quiet room. From the first stars exploding, seeding the foundations, to your pulse right now there is one very long, unbroken line. Call it an inevitable chance. Call it the grace of physical laws. Call it time's gift. Whatever the name, what matters is, we're here, still and listening, and, as the night deepens, hold this light thought, soft as dust. If every atom in you once lay in the heart of a distant star, then perhaps every kind thing you do, every gentle word you speak, is how those ancient stars go on shining, not in explosions, but in warmth. That is the deepest meaning of the Stardust journey. Not only spreading elements, but spreading the capacity for tenderness. Tomorrow, you'll wake and return to your familiar roads, your to-do lists. But tonight, sleep knowing you're a living thread in a story written with light and patience. Everything else, from cells to cities, from seeds to songs, is the epilogue of that first explosion. And here, on this thin edge between waking and sleep, we can smile to tell the story of life. The universe had to learn to write poetry with dust. My dear friend, before your eyelids grow heavy, I'd like to take you deeper into one small element that plays such an immense role that life on Earth, and perhaps life somewhere far away, leans on it. An element neither too rare nor too loud, not shining like gold, not magnetic like iron, not ominous like uranium. An element as modest as an old friend who knows how to stay by your side without ever showing off. Carbon. So what is it about carbon that the universe chose it as the primary language for writing life? Out of the hundreds of elements sprinkled across the galaxy, why is it carbon that forms cells, DNA, proteins, membranes, hormones, and ultimately our quietest thoughts? Why not silicon, which also builds beautiful crystals? Why not life based on ammonia or liquid methane, as some hypotheses suggest? To answer, we have to see carbon as a shape-shifting artist. Carbon doesn't just sit there on the periodic table. It loves to connect. It has 4 electrons in its outer shell, 4 empty seats in its tiny room, letting it bond to 4 other atoms at once. That special capacity, rare among elements, opens a vast playground. With those 4 seats, carbon can form every structure you can imagine: long chains, rings, branching trees, mesh networks, cage-like fullerenes, flat sheets like graphene. It can become porous, black charcoal, or the transparent diamond on your wedding ring long ago. But this isn't just a cute construction game. It's the gateway to the chemistry of life. Because of its bonding flexibility, carbon can build billions of distinct molecules, whereas silicon, its cousin, manages only a limited range of stable forms. Carbon is like a master potter shaping endless vessels. Silicon mostly repeats a few. Imagine the primordial ocean, warm, murky water, where molecules were constantly colliding. Each collision could break or forge a bond. Carbon is what lets those molecules not only exist, but tell stories. A carbon chain long enough, with the right functional groups, can carry information. Add aromatic rings, it gains chemical activity. Add branches, it gets more stable in water. Trim a piece, it becomes more flexible, able to fold and twist like a strand. DNA is carbon's masterpiece in that sense. But where did carbon come from? It wasn't there at the beginning of the universe. Back then, there was only hydrogen and helium. Carbon was created in stellar cores through nuclear reactions that fuse 3 helium nuclei into a single carbon atom. A process so delicate you might picture someone trying to press 3 raindrops into one bead. Most attempts fail. Yet in large stars, miraculously, it happens often enough that carbon-rich dust can drift across space. Those carbon grains became the backbone dust of planet-forming disks, of the first oceans, and eventually of life. When you take a deep breath, among the oxygen molecules float CO, 2 molecules bearing carbon atoms that have wandered for billions of years through countless storms of stars. What's charming is that carbon is vital not only as life's building block, but as a regulator of the environment that shelters life. In limestone, carbon locks away CO2 for millions of years. Plants pull carbon from the air, turning it into cellulose to hold themselves up. Our bodies burn carbon in glucose to power beating hearts and thinking brains. When you recall a childhood memory, it's billions of carbon-based molecules firing at synapses that let that moment bloom again. Carbon is not just a substance, it's rhythm and flow. Why does carbon work so well with water when life here is water-based? Because carbon-based molecules can survive in liquid water without falling apart too easily, yet remain reactive enough to change. They sit in a delicate middle ground, stable but not rigid, adaptable but not chaotic. That balance, somewhat durable, somewhat ready to transform, is the secret that lets life endure. If you listen closely, carbon begins to feel like an elder friend who understands balance. Not too hard, not too soft. Resilient without being stubborn. Flexible without losing itself. A quality humans often need half a lifetime to learn. Now, I invite you to close your eyes for a moment and picture the primordial oceans over 4 billion years ago. No city lights, no radio waves, no aircraft overhead. Just hot vapors rising from hydrothermal vents and falling back as heavy rain. In that water, carbon had already begun its puzzle, forming the first amino acids, then peptides, then molecules curling into rings, clustering into droplets, the earliest precursors of cells. Imagine it, an element that once burned in the heart of a star, now playing at building patterns on a seafloor. It's the longest, gentlest, and most glorious journey a speck of cosmic dust can take. At some moment, those folding carbon chains met in the right way, at the right time, to become catalysts, primitive proteins. Then, other complex carbon rings formed purines and pyrimidines, the alphabet of RNA and DNA. Carbon became the pen the universe uses to write its own story, and that story has never stopped. There's something almost poetic about carbon science. In pre-solar grains, preserved in the Murchison meteorite, scientists have found more than 70 kinds of amino acids, many not found naturally on Earth. Imagine that. A rock falling into an Australian field carrying an ancient chemical library, like a letter mailed from before Earth had oceans. Carbon inside that letter bears the signature of long-dead stars. If you sit one evening on your porch listening to the wind in the trees, remember that in every wood fiber, every leaf vein, every cell in your own body, carbon is quietly keeping things connected. It doesn't ask why. It doesn't demand praise. It just endures, steadfast and kind. We often think of carbon as heavy, as a culprit of climate change when it shows up as CO2. But that's only one chapter, and one we wrote. On the cosmic scale, carbon is the background instrument of life. If life were a song, carbon would be the deep strings holding up every melody. Now, listen to your body a bit. Your heartbeat, your breath, the comfort of your back against the mattress. All of that exists because carbon molecules are moving, colliding, and passing energy through countless tiny reactions inside your cells. Somewhere within you, glucose is breaking down in mitochondria, releasing energy so you can feel this moment. Carbon doesn't just form you, it keeps you being you. And the big, gentle question remains, if life exists beyond Earth, will it also be carbon-based? No one knows for sure, but the odds are high. Carbon is such a gifted actor that it's hard to replace. Astronomers have found carbon-based organic molecules in distant gas clouds, on comets, and on Titan, Saturn's moon. The universe seems to favor the same alphabet. Somewhere, in another corner of the galaxy, life may be whispering bedtime stories built on bending carbon chains, just as we are now. Before we end this part, keep one light thought close. Carbon is the bridge between you and the stars, not symbolically, but literally earthy and cosmic at once. A steady thread running from ancient stellar fire to your heartbeat tonight. In your dimly lit room, as your shoulders loosen and your eyes grow soft, carbon is still quietly working, keeping everything in you flowing, alive. It is the universe's memory resting in each cell. As you drift into sleep, those carbon atoms continue their story, and we'll walk into the next chapter together. But that's for later. My dear friend, each night, when you hold a glass of water and take a small sip before bed, you probably don't think much about the strange journey its molecules have taken. But in truth, what you're holding is history. Not a few hundred years like the stories in school books, but 4 billion years and more. A water molecule you drink tonight may once have been part of a cold interstellar cloud, millions of light years away, wandered between stars, slammed into forming worlds, and been heated to thousands of degrees in violent impacts back when Earth wasn't yet blue. So where did water come from? From deep inside Earth? From space? Dropped in as gifts from afar? Or both? And the most intriguing part, why did water arrive at just the right time, in the right place, in the right amount, to become the foundation for life as we know it. Lie down comfortably. I'll tell it slowly. Long ago, when Earth had just formed, it was nothing like the gentle blue sphere you know now. It was a molten world, glowing red, hammered relentlessly by countless bodies of all sizes. Young Earth was a construction site in chaos impacts. Heat, dust, water, in any familiar form, could not exist on the surface. The crust was hotter than a foundry, the air thick with rock vapor. Any molecule of water present would evaporate instantly. And yet, over time, water appeared. Not just a little, but an ocean's worth deep enough to drown continents, covering 3/4 of the planet. A volume so huge it's hard to picture. For decades, scientists have wrestled with the question. At the start, where did all that water come from? Two big ideas emerged. The first says water came from inside an endogenous source. As Earth formed from the hot disk of dust and gas around the young sun, some minerals trapped hydrogen in their crystal structures. As Earth cooled, those minerals released hydrogen, which met oxygen to form water. Volcanoes, in this picture, exhaled water vapor, Earth's warm breath. The second idea, more romantic and powerful, says water was delivered from the outside. Rocky asteroids and icy comets brought water to Earth after it formed. A period called the Late Heavy Bombardment may have dropped billions of tons of water here over millions of years. Picture that sky. Not calm blue, but a constant storm of incoming stones. Impacts lighting up the horizon. Not every impactor carried water. Not every comet came on the right path. Not every collision was gentle enough for water to survive. That subtlety makes people wonder, is there something that feels like destiny? A coincidence so beautiful it borders on poetry. Look closer, and reality is even stranger. A water molecule is 2 hydrogens and 1 oxygen. Hydrogen was born right after the Big Bang, and oxygen in later generations of stars. So the water you're drinking is a marriage of something very ancient and something younger. Hydrogen, perhaps nearly as old as the universe. Oxygen, maybe a few billion or a few 100 million years old, together forming a molecule that may have spent only a brief time in Earth's oceans. Some water came from space, some from within. By paths no one planned, they mingled. Is there evidence? Yes. Scientists compare the ratio of deuterium, heavy, hydrogen in seawater, to that in comets and meteorites. Some comets don't match, but certain carbonaceous chondrite meteorites, like samples fallen in the Sahara or Australia, have deuterium ratios astonishingly close to ours. At least part of our water likely came from them. Imagine those small, dark stones, loaded with ice, cruising for millions of years through cold, deeper than any Alaskan winter. One day, they meet a hot, trembling young Earth. Impact, melting. In the roaring fire, water is released, and this time it's held, not lost. Puddles form. Lakes, seas, here in your quiet night. Imagine the moment the ground first cooled enough for a drop of water to rest without vanishing. A tiny moment, but decisive. Like the second when you switch off the bedside lamp and the room settles into stillness. Now, leave Earth in your mind. Rise above the ozone, past the moon. Look back, a faint blue dot against black. That blue is water. Without it, Earth might look like Venus scorched, or Mars cold and dusty. Water makes Earth so distinct that people call it, tenderly, the pale blue dot. a droplet on the universe's palm. The most moving question, spoken slowly, is this: why did water arrive when Earth needed it? Too early, and it would have boiled away. Too late, and Earth might have locked into a dead, dry state. Too little, and there'd be no ocean to soften the climate. Too much, and pressure would crush the possibility. But somehow, it came. Just enough. Think of what water does for life. It dissolves salts, minerals, and amino acids. It stabilizes temperature. It lets molecules drift, collide, react, and try new combinations. Without water, RNA can't form properly. Proteins can't fold, and membranes can't close. Water is the stage. Molecules are the actors. Life's story is the play. Can you picture that primordial ocean? Darker than today's seas. Warmer, saltier. Lightning strikes the surface like a steady drum of energy. On the seafloor, hydrothermal vents breathe hot fluids rich in iron, sulfur, and manganese. Stable, energy-rich oases. There, water is not just liquid, it is a cradle. Some research suggests Earth's water is still being refreshed from within. Minerals deep in the mantle hold amounts of water comparable to the surface oceans locked in their structure. Volcanic activity releases a fraction of it. Breaths from Earth's interior. Water on Earth has never stopped cycling. It keeps trading roles between rock and sky. Every drop of tea you brew with may contain molecules that once flowed down the Nile, lay in Alaskan snow, beaded on roses in California, rose in a Florida summer storm. Its life is endless, never destroyed, only moved. Perhaps, as a child, someone told you, the water you drink might once have been in a dinosaur's sea. It sounds like a folk tale. It's scientifically true. On a deeper level, one quiet truth. Water links ages. Raindrops on your roof tonight may hold molecules from the very first rains on Earth. Water is liquid memory. Now, as your breathing slows, let me tell you why water is the strangest, most perfect liquid in the solar system. Given its size, water should melt and boil at much lower temperatures. Yet hydrogen bonds, tiny handshakes between molecules, hold it together, raising its boiling point, making it stable and heat-rich. Oceans don't scorch too fast in summer or freeze solid in winter. Water expands when it freezes, rare among substances, so ice floats. That simple fact lets life hide beneath ice in winter, instead of being entombed in solid cold. Without it, the first hard winter might have wiped the slate clean, and its shape, a bent molecule at 104.5 degrees. Not straight, not symmetric, just slightly skewed. That small bend, invisible to our eyes, is decisive for life. Have you ever thought that such a tiny angle could spell the difference between a living Earth and a dead one? Back to our question. How did water come to Earth? The loveliest answer is not from one place, but from many. From within and from afar. From icy comets, stony meteorites, deep minerals. Through countless routes, water came as a gift from many worlds, then joined to turn Earth into a rare blue gem. And finally, as you lie down and close your eyes, hold this comforting thought. Every water molecule in you, in blood, in tears, in brain cells, is the crystallization of the longest journey any tiny thing can take. Born in stellar hearts, drifting in space, locked in wandering rock, plunged onto a molten planet, boiled, condensed, rained, rivered, oceaned, and now resting as part of you. My dear friend, let me bring you back to a moment that seems infinitely distant, yet is bound to every cell in your body. A time when Earth was young, the sky thick with rock dust and heat, the sea not yet, the blue you know, but dark, dense, and far saltier. This was the primordial ocean, the very first cradle where life may have taken its earliest, tentative steps. Try to imagine this. No trees, no blue whales, no crashing waves like those mornings you once stood watching the ocean in California or Florida. Instead, there is an endless expanse of water, veiled in the warm mist of methane, ammonia, and steam rising from thousands of hydrothermal vents. That ocean is heavy with the smell of minerals, saltier than the water of today's Dead Sea, and the light of the sun is dimmed by a dense layer of gases, so that the whole planet seems to be trapped in a sunset that lasts for millions of years. Beneath that surface, wonders begin to unfold. When the Earth had finished forming its core and the crust began to cool, water condensed into oceans, curling into the fissures of the red-hot crust. At the deepest points, where geothermal heat drove out water hotter than 350 degrees Celsius, compounds like iron sulfide, hydrogen sulfide, carbon dioxide, and a host of other minerals mixed like a primordial soup, an ancient version of a cosmic chemical kitchen. And right there, in the very place where light could not reach, life may have been kindled. You can picture the deep sea floor as a universe of its own, so dark that if a human stood there, they would not be able to tell rock from water. The pressure is so immense that an ordinary steel vessel would crumple like paper. But in the hot water streaming out from the hydrothermal vents, molecules began to play at assembling. Metal ions acted as catalysts, allowing simple compounds to bind into longer chains. Amino acids, nucleotides, lipids, the first structures that knew how to cling to one another, to react with one another, to separate and recombine. The first breaths of a habit we would later call life. Some have hypothesized that hydrothermal vents are precisely where the first sufficiently stable chemical reactions took place for RNA to form. The natural mineral tubes in these vents, called porous chimneys, are only about as wide as a hair, yet inside those tiny pores, molecular concentrations could become high enough that reactions would not be diluted away by the vast ocean. And gradually, among millions of constantly colliding molecules, a molecule capable of self-replication appeared, a small spark in the depths of darkness. If you are listening on a quiet night, think of how it feels when you soak your feet in warm water, gentle, soft, fluid, wrapping around every curve of your ankles. The primordial ocean embraced those first molecules in just that way. Soft but not weak, dynamic but not chaotic. An environment so balanced that reactions could be strong enough to occur, but not so violent as to destroy everything. When the first lipid molecules formed, they self-assembled into thin membranes, like droplets of oil floating on water. No one instructed them to do so. There was no blueprint, but according to the laws of physics, lipids always turn their water-fearing tails inward and their water-loving heads outward, forming tiny bubbles with water trapped inside, a discrete chemical pouch, a first little home for life. And if you place your hand over your heart right now, you are touching the distant descendants of those lipid bubbles. They are the ancestors of cell membranes, the gatekeepers that regulate everything allowed to enter or leave each of your cells. But not every story unfolded at such depths. Some scientists believe life may have begun in shallow waters, where foam washed up and receded, leaving behind thin films of organic molecules clinging to rocks, a place where faint sunlight was enough to supply energy, but not so intense as to tear apart every chemical bond. Think of a quiet beach at dawn, waves gently gliding up the sand, breathing in, then drawing back, breathing out. The primordial ocean may have breathed like that, only slower, deeper, on a time scale of millions of years. And with each breath, as the water withdrew, it exposed small carbon chains stuck to rock surfaces. When they dried, they came closer together. When they became wet again, they reacted more. Like that, steadily, as naturally as the heartbeat of a sleeping person. That pattern of contract, expand, expand, could have driven molecules to self-organize into complex structures. RNA, peptides, prokaryotic membranes. Just like when you fold a wet towel and then unfold it, the creases remain. They do not disappear. The primordial ocean, too, created such chemical creases. Whether life began at the deep-sea vents or in the shallow waters along ancient shores, one thing does not change. It was water itself, the marine environment, that cradled those fragile chemical reactions, like a pair of hands cupping something easily broken. Have you noticed that whenever we retell the story of life, we keep returning to the ocean? Because the ocean is the mother of softness, of beginnings, of perseverance. And then, when the first proteins learn to fold, when the first RNA strands learn to replicate, when the first droplets of cells learn to divide themselves, the ocean had become the largest roof Earth ever had. Not hurried, not noisy, quietly nurturing. If you have ever stood before the sea on a summer night, when the surface is smooth as silk and the wind passes by like a whisper, you will understand why life chose the sea. The sea is soft, like sleep. The sea is warm like breath just before dawn. The sea is where everything could be tried for the first time without fear of breaking. But the primordial ocean was not only gentle, it was also full of challenges, more acidic, hotter, richer in metals. And it was exactly that fierceness that provided enough energy for reactions to occur. Life needed an environment just stable enough, and just wild enough. The primordial ocean was the perfect balance between those two. There is something few people know. The most ancient organisms we have found, archaea, carry a chemistry very similar to that of hydrothermal vents. The air means nothing to them because they arose when Earth had no oxygen at all. They live by drawing energy from reactions between hydrogen and minerals. They are ghosts of the primordial age still lingering among us. When you look at a photo of a sulfur-rich hot spring at Yellowstone, those orange, yellow-brown bands are the chemical signatures of such ancient-style organisms. You might think they are aliens, but in truth, every human cell bears the silhouette of that past. The way we generate energy with mitochondria is essentially the classic technique of bacteria. The way our DNA replicates is an echo of the very first RNA molecules. The way our cell membranes self-repair is the behavior of those ancient lipid bubbles. We are the primordial ocean walking in human form. And when we return to the image of gentle foam breaking over rock, we can see a quiet truth. The miracle lies in the small things, not in erupting volcanoes, not in falling asteroids, but in the repeated waves, steady and patient as breath, that sculpted the foundations of life. Life did not come from a single magical moment, but from millions of tranquil ones. One molecule meets another, One bond lasts a little longer than usual. One chain does not break. One droplet cell does not dissolve. Tiny moments, stretching across an unimaginably long time. And so we arrive here, tonight, listening again to that story. If you press your ear close to an empty seashell, you will hear the wind within it. People like to say that it is the sound of the sea, but to me, it is the whisper of billions of years. Folded into something small, the primordial ocean is still there, not only out there, but in every one of your cells. When you close your eyes, you are carrying the memory of the sea. The water in your blood was once water of the first oceans. The sodium in your body is the salt of the ancient seas. The flicker of ions in your nerve cells is the modern version of the electrochemical reactions that once took place near those earliest hydrothermal vents. We never left the sea. We simply carry the sea within us, and in the deep floor of that ancient ocean, where light never touched, but chemistry held steady, life began with three things: patience, chaos, and a little luck. Just like you, tonight, letting go, letting your heart slow down in the quiet of your room. A gentle, vast quiet, like the very ocean that has cradled life since the earliest days, from the place where silent reactions once stirred the first organic molecules. The story shifts its rhythm slightly. If there was already a chemical soup and wavering RNA strands, what turned randomness into a within and a without was the moment when a tiny droplet sealed itself, enclosing its own little world, the moment life whispered its first word. Imagine this: in a warm puddle on an ancient shore under a sky still heavy with ultraviolet light, or deep below the sea at a hydrothermal vent, patiently exhaling warm fluids, simple, fatty molecules, fatty acids, drift lazily. They need no guiding hand. All they need is water, a little salt, a little thermal motion, and it is enough for the water-fearing tails to shy away from the waves, the water-loving heads to face outward, and then, like a flock of birds drawing in their wings, they self-assemble into membranes, where they fold into closed loops. Some patches curve into perfect little circles, forming tiny two-layered bubbles, vesicles minuscule, transparent like dewdrops. This is the miracle of self-organization, a gentle law of physical chemistry. When the ingredients and conditions are right, order arises from chaos. Quietly, steadily. Where did these fatty acids come from? In meteorites that fell to Earth, scientists have found simple organic molecules, both amino acids and fragments of fatty acids. In volcanoes, in lightning flashing through the primitive atmosphere, in reactions between iron-sulfur minerals and carbon dioxide, small carbon frameworks could form. Once present, they self-assemble. In shallow ponds, wet, dry, and hot-cold cycles of day and night help membranes practice breathing. When the water recedes, membranes pack tighter. When it rises, membranes swell, swallowing molecules from outside. In the deep sea, pores in rock provide ready-made micro-pockets, natural molds for fragile new membranes. Whatever the scenario, the principle is the same and gentle. A thin boundary appears so that the world can have an inside and an outside. That boundary, a membrane, is not just a fence. It is the conductor of concentration. Inside a droplet, organic molecules suddenly lie closer together, colliding more often, making reactions more likely. Certain clay particles, like montmorillonite, can serve as workbenches, catalyzing the elongation of chains. For example, RNA. When a short RNA fragment is present inside a droplet, it does not drift away immediately. It is retained, pampered by proximity. If a ribozyme, an RNA that can catalyze reactions, finds its way in, that droplet gains a skilled worker. Among countless droplets, a precious few can replicate short sequences faster, endure heat and salt better, and so, natural selection at the droplet level can softly begin. But life is not just information, it is energy, those tiny ion currents in the dark. In the ancient ocean, alkaline hydrothermal vents created natural pH gradients, warm, alkaline inside, more acidic outside, an inherent proton slope. Today, every one of our cells lives by an elegant version of that slope, pumping protons across the membrane and letting them flow back, like a tiny stream turning the ATP mill. Perhaps before a complete protein turbine existed, cracks in rock, natural mineral channels, or small peptides pitting the membrane already allowed protons to pass. A free energy gradient out there, a primitive membrane able to exploit the difference. And the reactions inside gain a gentle backing. Picture a protocell droplet resting in porous rock, each flush of alkaline water over it, a quiet recharge in the deep sea silence. In parallel with energy came metabolism, efficient chemical shortcuts, a few ancient CO2, fixing cycles, like the acetyl-CoA Wood-Ljungdahl pathway, may have emerged on iron-sulfur mineral surfaces. Those iron-sulfur clusters later became ornaments in countless modern enzymes. In that early gloom, such reactions may have taken place outside membranes, then were gradually imported into droplets. As membranes learned to embed charged molecules, each droplet was a tiny experiment on a vast planet. If a network of reactions produced molecules that made the droplet more salt-resistant, it survived longer. If reactions created new fatty acids that thickened the membrane, the droplet swelled and then divided. No intention was needed, only convenient cycles of growth and division, and already there was a distant echo of reproduction. Pause for a moment, will you? Picture the moment a membrane learned to grow. In an environment scattered with fatty acids, droplets richer in longer chains inside tended to draw in more fatty acids from outside, like a thirsty person pulling water into their cup. The membrane loosened, the droplet inflated, then a small wave, a knock against rock, and it split. Two daughter droplets sharing the same inside, a bit of RNA, a little sugar, some salts are divided between them. Each time it worked, that family of droplets grew. What we now call heredity was crude but already there. The chemical composition inside bestowed the capacity to capture fatty acids, retain energy, tolerate salt, and those capacities, though born of chance, were still passed on. One major obstacle for RNA and water is Mg² mice ions needed for replication, yet capable of disrupting fatty acid membranes. But nature has a buffer. Complexing agents like citrate can bind Mg² mice, just enough to keep it useful without tearing membranes apart. At lime-rich riverbanks, in mineral-laden pools, a droplet with citrate inside suddenly has an advantage. It both replicates RNA well and keeps its membrane intact. Another soft tick of selection. In many hypotheses, some propose a lipid world first, others favor an RNA world, or metabolism first. But if we press our ear to the ground and listen, we hear a shared melody. Life is a chorus. Membrane, metabolism, and information never stand alone. They grow by leaning on one another. Membranes protect reactions. Reactions generate components that sustain membranes. RNA remembers efficient reaction steps. Ribozymes open new shortcuts for energy. Short peptides, formed by chance, punch tiny channels in membranes to let ions pass in a measured way. When a droplet exploits protons better, it makes more proto-ATP, energy coins. With peptide channels, its proton gradient becomes more refined. With primitive enzymes, carbon fixation runs smoother. Small rungs, but a ladder that can stretch without end. In everyday life, there are moments much like this turning point. A solid porch lets a whole house be lived in. A small wallet holds scattered things, and suddenly life feels organized. The primitive cell membrane was the wallet, the porch roof of the chemical universe. From the moment it appeared, chemistry no longer lay flat like a desert. It became countless oases, each able to guard secrets, nurture better formulas, and then pass them on. Another gentle knock at the door. Deep sea or shallow pond. In the deep, the proton gradient is ready-made. Minerals abound. Temperature is stable. In the shallows, wet-dry cycles concentrate and link molecules. Light triggers reactions. Rain brings fresh inputs. Perhaps both are right, at different times and places. The ancient Earth was wide enough to run all experiments in parallel, and somewhere, some paths met. Droplets in ponds learn to create their own proton gradients. Droplets at vents learn to cope with changing surroundings. The world did not choose a single road. It laid many to raise the odds of blossoming. Within those droplets, structures grew more diverse, more complex. Phospholipids emerged, replacing simple fatty acids, making membranes sturdier, less leaky. Short peptides proved surprisingly useful as doors for ions, sugars, and nucleotides. Some peptides would later evolve into proton pumps, into ATP synthase, the miraculous mills of the cell. Perhaps at first, peptides formed accidentally during wet-dry cycles. Amino acids dried on the hot rock, linking into chains. When a few chains happened to lodge in membranes and form pores, droplets with them survived better amid fluctuating salinity. And so, peptides were kept. So, do you hear the rhythm of time? Each dawn, droplets warm and reactions speed up. Each night, they cool and reactions slow a breath. Each dry season tightens membranes. Each rainy season swells them a step. From that rhythm, reaction networks begin aligning with day-night cycles, with tides. Natural rhythms are becoming biological rhythms. Though mindless, droplets learn to heed their environment and adapt. On the side of information, RNA strands gradually formed more reliable pairing habits. Hairpin loops grew more stable. Repeating motifs were easier to copy. But this came with the problem of errors. At tiny scales, with slow rates and many mistakes, only reaction networks tolerant of flaws could survive. Life chose resilience over perfection. Later, when enzymes, ribozymes, then proteins arose, error rates fell, and the music gained more voices. Let us pour into this imaginary cup a brief stillness. In the darkness of that first night, with membranes, it is as if someone had quietly closed a door so that a small candle, not yet aflame, could burn without being blown out. That candle was the proton gradient, a few RNA strands, and a handful of metabolic side reactions. By morning, a soft wave split the droplet, each half carrying away part of the glow. Everything is still fragile, but a long enough chain of days would let fragility mature into endurance. At this point, we can place a hand over our chest and smile. Every heartbeat we have today is an heirloom of chemiosmosis, that ancient proton flow refined. Every cell in our body, with its smooth phospholipid membrane and spinning ATP synthase, is a luxurious descendant of that first droplet. When you see soap bubbles in sunlight, or a bead of oil curl within broth, you are seeing reflections of that beginning. The world has never stopped retelling its origin in small, simple details. Of course, many puzzle pieces remain blurred. Which came first, membrane, metabolism, or RNA, has no final verdict. But the beautiful truth is, they helped one another up. That mutual support chemical symbiosis is a lifelong theme of biology. Later, symbiosis would reach even deeper. One cell engulfed a bacterium, and the two never parted. We call it the mitochondrion, but that belongs to later chapters. Tonight, it is enough to know that, in the quiet of water and rock, the universe tried billions of times to produce a droplet that could hold energy, guard its secrets, divide, and once that effort succeeded, if you are lying on your familiar bed, listening to the steady hum of the ceiling fan, think of the ancient deep sea as a great chamber of time. There, the little droplets were never rushed, never loud, only patiently learning how to become an inside. Through each long night, they picked up one more trick: how to take in fatty acids, how to keep mg² mice without tearing their membranes, how to use a proton gradient to drive a difficult reaction, how to divide without losing what mattered. Every skill your cells now possess, one by one, had its seeds in those droplets. And so, it turns out Stardust is not just about elements. Stardust went further, becoming membranes, becoming boundaries that know how to cradle what lies within. Chemistry became packaged, energy gained wires, and information gained a shell. The step from the boundless to the bounded, from open water to tiny droplets, is the step that made life possible. Night slows, breath slows, and we can clearly feel the gentle warmth of a newly built home. In time, the story will carry us to the moment the sky changed color, when oxygen flooded the air, when cells learned to wield light. But before that dawn opens, let your heart rest with the image of a clear little droplet, quietly swelling, dividing, swelling again. Life is not thunder, but long rain on a tin roof, very soft, very steady, very persistent. And from such a fragile droplet, at last, after so many nights, we the listeners here have arrived. My dear friend, try softly closing your eyes and take a light breath. That breath, even if you hardly notice it, is the gift of a revolution so ancient it defies imagination. A revolution without gunfire, without pounding footsteps, without a single cheer, only small ripples, tiny bacteria, and time stretching over hundreds of millions of years. Before there was free oxygen, Earth was a planet of dissolved iron, of deep blue oceans almost black, of an atmosphere thick with methane and CO2. The air then was not breathable at all. If you were brought back to that time, those ancient spaces would be a heavy curtain pressed over your lungs, where every breath would be nothing more than a brief hope. But in that world, tiny organisms were quietly doing something unprecedented, capturing light and splitting water to make energy. Simple cells bearing green pigments, cyanobacteria, had learned to use light as their own private flame. They drew CO2 from the water, used photons from the sun to pull electrons from water molecules, and from that process, they released something that had never before existed in the young atmosphere. O2. Your breath is the echo of their breath from billions of years ago. Strange, isn't it? Earth did not have oxygen from the beginning. Oxygen was not originally available in the oceans or the air. Oxygen was created by life, not the other way around. So let me tell you, slowly and gently, about the longest dawn in this planet's history, the Great Oxidation Event, which took place about 2.4 billion years ago. Imagine the oceans back then, a still surface, heavy with the smell of dissolved iron, light piercing that murky water, just enough to weave a faint green curtain at ancient noon. In that dim water, cyanobacteria formed thin mats like soft cloth laid over rock, layer upon layer, in silence. Each day, they photosynthesized. Each day, they released oxygen, but oxygen could not accumulate right away. It met dissolved iron in the sea and reacted, forming iron oxides that fell to the seafloor like red dust. We can still find traces of that time in banded iron formations, red and black layers, stacked like giant marble slabs of time. Oxygen was produced, then vanished, then produced again, then completely consumed, like a breath caught in the chest of the ocean. But cyanobacteria did not stop. The sun kept shining, they kept living, and eventually, oxygen became so abundant that there was no longer enough iron to swallow it all. For the first time, oxygen began to leak into the atmosphere. Can you picture that event? No fireworks, no sound, only tiny O2 molecules, drifting, patient and slow, and gradually transforming the entire planet. As oxygen began to accumulate, methane, a powerful greenhouse gas, was broken down by it. That made Earth grow colder, colder still, very cold. Some evidence suggests that Earth may have gone through a snowball Earth phase when ice covered nearly the entire surface of the planet. Think about it. Oxygen, the thing that keeps us alive, that keeps the candle of consciousness burning bright, once nearly froze the whole planet solid. But that cold was also a trial. It favored organisms that could tolerate low temperatures, use oxygen, and create antioxidant enzymes. The weaker ones, the oxygen-shy ones, ultimately vanished or retreated into dark corners, becoming the anaerobic microbes we know today. Life chose a new path. Why is oxygen so important? Because oxygen is the most powerful electron acceptor that life can conveniently use. By using oxygen to generate energy, cells can produce many times more ATP than with anaerobic methods. That opened a new horizon. Larger cells, more complex cells, cells packed with internal structures. If you like images, before oxygen, life was like small houses lit by flickering oil lamps. After oxygen, life was like a city wired with electricity. Light no longer stayed in just one corner. It spread throughout the whole body. Oxygen also led to another turning point. The emergence of eukaryotic cells. Cells with nuclei, with mitochondria, with internal compartments. And mitochondria, are in fact the descendants of an ancient bacterium that had already mastered using oxygen to generate energy. In your body, in every cell, mitochondria are still breathing oxygen, spinning the rotor of ATP synthase, generating energy for every heartbeat, every thought, every dream you carry into the night. The arrival of oxygen did not just turn Earth from black to blue, it turned life from simple to complex, from unconscious to conscious, from deep ocean to dry land, from silence to birdsong, footsteps, and the whisper of wind. Have you ever thought that the blue sky you see each morning is, in part, the consequence of cyanobacterial breath from 2.4 billion years ago. Soft, isn't it? A breath from creatures smaller than dust changed the fate of an entire planet. As oxygen flooded the oceans, minerals changed color, iron precipitated out, and the seas shifted from deep dark blue to lighter shades, then gradually to the turquoise we know. The atmosphere cleared. Light penetrated more deeply to the surface, opening the way for plant photosynthesis later on. Plants did not invent photosynthesis. They inherited an ancient algorithm, the same mechanism, chlorophyll, electrons, photons that cyanobacteria had used long before. Plants simply expanded it, lifted it onto land, painted forests into being, cast shade, and spread oxygen still farther. But perhaps the most beautiful thing about oxygen's appearance lies in its silence. Nothing about that event was rushed. Nothing about it was dramatic in the way we humans usually imagine. It unfolded slowly, like rain seeping into soil, like mist sinking into valleys. Try imagining yourself standing on a primordial shore. Very early morning. The fog is still thick. You lean down toward the water's surface. Beneath the faint ripples, cyanobacteria are quietly working. No one instructs them. No one observes them. And they continue to photosynthesize for millions of years, cautiously lifting oxygen above the sea. They do not know they are changing the entire planet. They are simply living the way you breathe, the way the sea murmurs at night. There is one more curious thing. Oxygen not only nurtures life, it also harms it. Oxygen creates reactive oxygen species ROS molecules that can damage DNA and proteins. Life had to learn to cope. Catalase, superoxide, dismutase, and countless antioxidant enzymes arose. Thanks to them, life learned to turn something dangerous into something useful. That too is the art of biology. Not eliminating danger, but learning to lean with it. Tonight, as you lie there listening to me, try to notice for just a second. You are alive thanks to something that is both savior and threat. Oxygen is light and flame at once, like all the most beautiful things in this universe. And slowly, oxygen stopped being something new. It became the backdrop. It was woven into the atmosphere as background music for terrestrial life, for the wings of birds, for the lungs of animals. Oxygen is what lets you light birthday candles, strike a stove's flame, or simply take a deep breath beneath a tree. And the most wonderful part? It all began with a few tiny cells that knew how to catch the light. Night is settling softly, and so is the story of oxygen. You don't need to remember every date, every enzyme's name. Just remember that the breath you are taking right now is an ancient gift, crafted over billions of years of patience and quiet work. And if you listen carefully, deep within that steady rhythm of your breathing, perhaps you will hear an echo of the ancient sea, of small cyanobacteria, quietly using light to do the greatest thing life has ever done. From the place where silent reactions fell into rhythm, from the chemical mist whispering beside primordial shores and vents, the story shifts gently again. If the letters and first tones of life's melody already existed, then who was the very first musician? Was there someone standing in the prehistoric fog, gathering stardust into a steady flame called life? We give that someone a name that is both scientific and strangely soothing. Luca, the last universal common ancestor. Luca was not a single individual as often drawn in textbooks. Rather, it was a fragile population. A tiny clan of microbes living when Earth was still very young, more than 3 billion years ago. Luca is like a river junction where the currents of the universe elements, energy, order, met, and then flowed out into countless large and small branches. To tell Luca's story is to tell how Stardust was packed into a toolkit, a genetic code usable everywhere, a shared energy currency, a tiny furnace inside every cell, and a peculiar but useful habit to exchange, borrow, even steal one another's ideas to survive. Let's begin with one tool from that kit, the ribosome, the machine that reads life's score. In every modern cell, from soil bacteria to your liver cells, ribosomes sit like old record players, both sturdy and exquisitely detailed. They read RNA letter chains, 3 bases at a time, and stitch them into proteins, muscle fibers, digestive enzymes, structural proteins, hair, nails, memory. The structures of ribosomes in bacteria, archaea, and in us differ a little, but their core and rhythm of reading are nearly identical, as if the great orchestra of life all plays from the same clef, set down in a very, very distant age. What does that commonality suggest? That Luca already possessed a sufficiently complete type of ribosome to pass on to all descendants, and ribosomes, intricate as they are still made of stardust, phosphorus in the RNA backbone, nitrogen and carbon in the 4 notes A, U, G, C, and metal ions, magnesium, zinc keeping the player running smoothly, all born from dead stars, scattered by the universe. In Luca's toolkit, there was also a shared currency, ATP. Those 3 simple letters are warm little coins paying for every energy-demanding act. Opening ion channels, transporting nutrients, mending tears, and copying memory all require ATP. Intriguingly, the way ATP is earned harkens back to the deep forges of Earth's crust. Luca most likely lived in neighborhoods rich in hydrogen and CO2, where hydrothermal vents at the seafloor created natural proton gradients between inside and outside a built-in energy slope. On that slope, protein turbines turned slowly, like windmills in the morning mist, converting proton flow into ATP coins. In other words, Luca knew how to live by something very universal: potential differences, slopes rising and falling, like rivers running to the sea, like wind blowing from high pressure to low. When you breathe evenly and your heartbeat slows before sleep, the tiny factories in your cells are still spinning quietly, using that same ancient currency, a gift of stardust passed through rock, through salt water, through billions of years. If there is a record player and a currency, Luca also needs a rulebook, the genetic code. Strangely, almost all organisms on Earth use essentially the same translation table. Triplets code for amino acids, 64 codons, 20 bricks of proteins. Why the same table? Because patterns that arise early, are stable, and work well tend to be kept. Luca settled on a code very close to the one we use today, and all its descendants, from algae to giraffes, rarely change the rules, because changing them would be catastrophic. To put it in homely terms, once a whole town has learned to drive on the right, switching to the left invites chaos. Life, similarly, chooses the path of least ruin, but an ancestor also needs a home. Luca's home was a membrane, a thin layer of molecules that love and hate water, self-closing like a dewdrop. Those early membranes may have been delicate, sometimes porous minerals at hydrothermal vents, sometimes self-assembled fatty bubbles. Within such environments, Luca learned to keep the inside different from the outside, to open and close the door as needed. And in doing so, information had a place to rest, energy a place to be transformed, matter a place to be arranged. If you are lying there with eyes closed, picturing a night-smooth water surface, then a faint breeze making soft ripples. The cell membrane is just that, a slim fold between chaos and order, between out and in. Let's take one more step to a deeper fold. Exchange and borrowing. In Luca's time, the biological world was not as neatly divided as today. Tiny families swapped genes like villagers sharing rice seeds. If one had a useful metabolic enzyme, a neighbor might pick it up via drifting RNA fragments or primitive viruses. Luca was thus not a pure, isolated lineage, but a crossroads where many streams of information mingled and parted. You see, life's story is not solemn and sealed. It's more like a marketplace, warm and busy, where the goods are gene cassettes, the craftsmanship is enzymes, and the rule is, if it works, it stays. Here, Stardust steps back onto the stage. The most crucial enzymes of energy metabolism, those first chefs, rely on clusters of iron, sulfur, nickel, molybdenum, heavy metals, forged in supernova explosions. They are tiny, bright cores in enzyme hearts, conducting electrons like copper wires in your walls. Thanks to those cores, humble hydrogen and CO2 become acetate, amino acids, and the foundations of lipids. Close your eyes for a moment, and you might hear the soft crackle of an ancient stove, smell warm iron and a hint of sulfur, like the scent of the first rain on a tin roof. That stove is cooking the starter soup from cosmic ingredients. You might ask, what did Luca look like? It does not appear in fossils like dinosaur bones. Luca left its traces in how we all function. Those traces are the shared genetic code, the ribosome, the ATP synthase turning like a mill, and the strangely similar metabolic shortcuts from bacteria to humans. If we drew the kitchen layout of every species, we'd see familiar spice jars, the same pots and pans, placed in almost the same spots since long ago. Luca, in that sense, exists in every cellular meal you make, in every breath, every yawn before sleep. When we tell each other bedtime stories, we often end up with family trees. The family tree of life is long and full of bends. After Luca, two great clans, bacteria and archaea, wandered very far in different directions, and only much later birthed the nucleated cells to which we belong. But even as they parted, they carried Luca's tools. Why? Because those tools were efficient, economical, tested in the furnaces of the seafloor, in the roar of proton flows, in salt and darkness. The common ancestor did not teach us everything, but it taught the most essential lesson: how to keep a small flame burning steadily, even when the wind shifts. There is a detail rarely mentioned, but quietly poetic. Life seems addicted to gradients. From proton gradients across membranes to salt gradients, electrical potentials, and temperature differences. Luca lived among the natural gradients of the young Earth, then learned to build its own gradients when it moved away from the vents. Have you ever leaned on a hillside and felt your body lighten as the slope takes some of your weight? Cells do the same. They lean on gradients to save effort, so their tiny wheels can keep turning. That is the clever habit Luca passed down. Don't fight the world, borrow its force. At night, we tend to think of home, Luca's home was a dark ocean, and its neighbors were porous rocks full of tiny cavities. In those minuscule chambers, warm mineral-rich water flowed, carrying iron, sulfur, nickel. They formed scattered laboratories on the seafloor, where reactions happened slowly, repeatedly, enough for rhythms to emerge. Imagine those chambers as honeycomb cells, each one a dream gradually taking shape, and one of them becoming Luca's first shelter. That shelter was not romantic in the sense of starry skies, but it was warm, stable, durable, and above all, repetitive. Every rhythm you love, from a living room clock to your heartbeat, grows from repetition. Life, at its core, is the art of repeating without becoming dull. Then one day, meaning millions of years, those first dwellers left their mining village on the seafloor, carrying with them the discipline of proton gradients, the iron-sulfur stove, the genetic reading rules, to venture into different waters, different lights. They wrapped themselves in better lipid membranes, managed energy more skillfully, and learned to harvest light or hunt chemical prey. Some lineages failed, disappeared. Many succeeded, and the family tree grew taller and broader. Thus, Luca's story slipped into the background, like a deep bass line beneath every song. Rarely noticed, but without it, the music falls apart. Now, let your eyes rest on this image. You lying in bed, blanket light upon you, window still. Outside, the city's sounds thinning out. In that quiet, your liver filters blood, your heart keeps time, and tiny ribosomes are still knitting fresh proteins. All of it continues in silence, just as Luca once lived, persistent, frugal, cooperative. The stardust in you does not sleep. It only lowers its voice, working steadily, like an old craftsman under lamplight. If you'd like to touch a little deeper, we can ask, why did the universe choose life? The humblest answer is, it didn't choose, it allowed. Wherever energy flows, matter is plentiful, and there are surfaces and small compartments to keep reactions from diffusing away. Order can emerge. Luca was such a flame of order, self-sustained by passing energy, self-reinforced by cosmic materials, and once lit, the flame sought ways to burn more steadily, more enduringly. That is evolution. So when we say we are made of stardust, it is not only because the atoms in our hair and blood were once stellar ash, but because the operating rules of stars, flow, fusion, balance have been translated with exquisite subtlety into the rules of cells. Dear listeners of this channel, especially those ears that have heard many autumns fall, perhaps you feel how human this sounds. We live well when we conserve strength, borrow force, cooperate, and keep the habits that have proven their worth. Luca, tiny and remote as it is, teaches that, through its very structure, from Luca to you, the thread has never snapped. The same ATP pays, the same ribosome sings, the same code underlies the text of your life. And finally, let's keep a small pause. Breathe in, breathe out. Do you hear? Deep down where your stomach is warm and your chest rises and falls, an ancient rhythm continuing. It is the rhythm of proton gradients, of ATP wheels, of ribosome song, of the three-letter code, all the things Luca once bestowed. Outside your window, the night is fit for remembering stardust. Inside your body, stardust is working for you, quietly. When you slip into sleep in a little while, know that every cell is still tending the fire, tending the stove, like those ancient workers by the sea vents. and that tomorrow's dawn, whether it belongs to you or to another generation, will still find that fire warm. We, in the gentlest sense, are descendants of a river junction called Luca. At that place, stardust stopped drifting and became home. Energy stopped wandering and became a gentle current. Letters stopped being meaningless and became words. This story does not require you to grasp every detail. It only hopes you can hear the deep consistency that lulls you. Life is an ancient song, and Luca is the opening refrain, low yet steady, simple yet endless. Let that refrain carry you lightly through the night, in gratitude for the stars that died so we could shine in our own way. And as the story comes to a close with the atmosphere transformed, the young ocean stirred, we pause for a single breath. But how did life turn its course from simple unicellular forms to complexity? Was it a single act of swallowing one another that opened the door to a new era? From the briny tidal zones where life first hesitantly left the water for land in the previous part, we gently lean forward and step on. Who kept that fragile candle from going out in the cosmic winds? Who drew the clouds at just the right moments, shielding the young world from bursts of solar fire when the sun was still temperamental? Tonight, we listen to the story of the invisible guardians, patients like lighthouse keepers along the Atlantic coast, blinking steady beams so the ships of life can follow the channel and arrive safely. Perhaps, when we think of the origin of life, we tend to focus on chemical reactions, warm oceans, and self-replicating molecules. But before all those subtle things, life needed a home calm enough not to be swept away by the storms of space. The universe is beautiful but wild. Meteor storms, radiation, solar wind were long-standing trials. And yet for billions of years, Earth has kept clear skies, warm waters, and regular seasons. The secret lies with 4 gatekeepers: the moon, the magnetic field, the atmosphere, and, far away, the giant planets. Let's start with our most familiar companion, the moon. On a quiet American night, when you open the back door and look up at the full moon like a silver disc, you may not realize the delicacy of the task it performs. The moon is like a gentle hand resting on Earth's shoulder, keeping its axis from wobbling too wildly. If the tilt shifted chaotically, the seasons would leap in turmoil. Sometimes endless summers scorching like deserts, winters freezing deep into low latitudes. Young life would struggle to cope with such dice roll weather. But thanks to the moon, Earth's axial tilt drifts slowly, softly. The seasons come and go like a classical piece, with phrases and refrains, giving plants and creatures time to adapt. Not only that, the moon's tidal pull breathes in rhythm with the oceans. High tide, low tide, tidal flats exposed and submerged, becoming chemical cradles where molecules meet, part, and pair up. Many scientists believe those warm tidal zones contributed a crucial low note to the overture of life's origin, like a pause in a lullaby, not loud but essential to the music. Tides, rising and falling over millions of years, also erode coasts, carry minerals to the sea, and nourish nutrient cycles. And more quietly still, through tidal friction, the moon slows Earth's rotation a little, helping establish a stable day-night cycle, so biology can set its internal clocks. From the moon, we listen deeper to the murmuring of the planet's iron heart, that is Earth's magnetic field, born of a molten iron-nickel core in motion like an ocean of metal. Imagine another lighthouse, not of light but of invisible field lines, bending the solar wind streams of charged particles hurtling in at insane speeds. Without a magnetic field, those winds would scour the atmosphere like sandstorms, stripping away lighter molecules, thinning the air that warms and shields the surface. On northern nights, when you see auroras in green and violet draped across the sky like silk, that is the frontier where this gatekeeper is at work, deflecting charged particles, letting them dance in the high sky instead of unleashing a rain of radiation on the ground. Under that protection, Earth's surface is far gentler. DNA is less battered, cells less shattered, the delicate embryos of life allowed to sleep safely and grow. One layer deeper is the atmosphere, the planet's soft quilt. High up, ozone acts as a specialist gatekeeper, blocking much of the fierce ultraviolet. Lower down, molecules like water vapor, CO2, methane, do the just enough job of retaining warmth, like an electric blanket set on level 1 inch. A cold night, not too hot, not too cold. If the quilt grew too thin, Earth would shiver like a frozen desert. Too thick, and the planet would burn with a fever. The marvel is that this quilt has self-adjusted, largely thanks to the carbon-silicate cycle. Mountains uplift, weathering and rain wear them down. Rivers carry ions to the sea, sea floors bury carbon, then inner heat uplifts crust. Volcanoes release some carbon back to the air, a long, slow breath over millions of years, like a kind old person counting each breath in the dark. Steady, patient, balanced. That breath could not run if Earth were only a dead rock. Here, the living architecture of geology, especially plate tectonics, does the work of slow pumps. Continental plates slide, collide, and subduct, dragging carbonate sediments down. Oceanic plates spread, bringing hot material up. This motion keeps the planet supplied with young mountains to weather, deep oceans to store carbon, volcanoes to exhale gas, a long-term thermal regulation system. With only still oceans over an immobile crust, heat would redistribute poorly, nutrients would get stuck where they accumulate, and the cradle of life would soon grow poor. On Earth, everything is stirred just enough, like you gently swirling a spoon in your afternoon tea, letting the sugar dissolve evenly and the fragrance spread softly. Step farther out and we meet the gas giants, Jupiter, Saturn, standing at the outer edge as far sentry guards. In many models, their gravity stirs, gathers, or even slingshots the orbits of countless icy bodies. Sometimes that means sweeping big impactors away from the inner system, reducing extinction-level collisions. Sometimes it means flinging extra packages of water and organics inward unasked for, but precious gifts. The truth is subtler than a neat fairy tale of an absolute shield. Those giants both protect and test, both clean the path and send more material in. But over deep time, their presence helps shape a stable orbital architecture. So rocky planets like Earth don't have to exist in a slum of random icy bullets. Perhaps that blend of shelter and trial enriched the stockpile of raw ingredients and gave life a chance to evolve, challenged just enough to grow stronger, but not so much as to be erased. And then there is the sun, the central flame, a mother both warm and capricious. In the distant past, the young sun breathed hard, flaring strongly. Later, its rhythm softened, its 11-year cycles becoming clock-like. Earth sits at a golden distance, close enough that water does not remain permanently frozen, far enough that it does not boil away. When the sun was dimmer than now, The faint young sun paradox was eased in part by stronger greenhouse gases and deep oceans holding heat, like vast warm basins. As the sun slowly brightened over billions of years, rock and life cycles drew down CO2, cooling things just enough. It is all like a waltz of balance. One side warms, the other side soothes partners so attuned they hardly need words. You might ask, aren't all these factors just accidents? Yes, chance plays a big role, but not mere blind luck. The laws of physics set a spectrum of possibilities. Planets large enough can hold atmospheres. Those with molten metallic cores can generate magnetic fields. Those with liquid water and plate tectonics can regulate climate. In the cosmic garden, many blossoms might open from similar recipes. Modern telescopes are finding thousands of exoplanets, some Earth-sized, some in habitable zones. This does not make Earth less special. If anything, it warms the story we tell tonight. We are not alone in nature's formula, but the way the ingredients harmonize here with an unusually large moon, a strong magnetic field, persistent plate tectonics is unique enough to invite gratitude. Let's touch, softly, the oceans, the planet's great shock absorber for climate. Water has a high heat capacity, meaning it takes much energy to heat up and cool slowly. In the furnaces of supernovae, heavy elements like iron, calcium, phosphorus were forged. Earth inherited just enough to have a solid core, rocky crust, and nutrients for cells. Phosphorus to bind energy into ATP, iron to carry oxygen in blood, calcium to build bones. All gifts of ancient stars that only unfold properly when the planet's frame is built just right. From time to time, the universe knocks with a major impact. We do not dodge them all. Earth's history bears record of mass extinctions, but strangely, between such losses, life's story turns new ways. Some lineages perish, others rise, and the emptied spaces become stages for novelty. Perhaps it is precisely those guardians, the moon, the magnetic field, the atmosphere, the giants that softened the blows, so that instead of shattering everything, ecosystems could spring back like a blade of grass after a heel steps on it. Like stumbling on thick carpet, you still fall, but it is softer, safer. In tonight's bedtime story, there is one image I'd like you to keep. Against the black of space, Earth is a lit island. Around it, there are breakwaters of magnetism. A lunar lighthouse, distant patrol ships in Jupiter and Saturn, and a warm atmospheric wall. Inside the island, rivers, forests, and singing rains link day to night, one season to the next. You, a body made of stardust, are lying here, listening, breathing in and out slowly, in sync with the planet. You may wonder, what if one guardian were missing? Without the moon, Earth's tilt might wobble more wildly. Without the magnetic field, the solar wind might strip the air. Without the distant giants, meteor storms might strike more often. Without plate tectonics, climate regulation might falter. None of these is a strict all-or-nothing switch, but with each piece weakened, the planet grows a bit more precarious. Life might still sprout, but it would be harder for it to bloom into a lush garden like the one we see today. And you might also ask, are we a rare case? Here, science and humility meet. We do not know yet. New telescopes will show us worlds with big moons, with magnetic fields, with seas. Each discovery may add a new verse to humanity's long lullaby. Until then, gratitude is the most reasonable response. Grateful that we have a deep blue night sky where the moon rises and auroras burn. Grateful for seasons that shift as gently as a scarf over shoulders. Grateful that, amid cosmic winds, invisible hands keep life warm. The night in America is long and soft. If you're in a small Midwestern town, maybe the wind turbines are spinning outside. If you're in New England, waves are whispering at the foot of lighthouses. If you're in the South, fireflies are shimmering in the yard. All those images are small metaphors for the great guardians. Steady rotation, guiding lights, gentle glows. Keep that image with you as you close your eyes. Let your heart beat to the slow rhythm of tides, fields, winds, and far-off planets. Because in the end, the story We Are Made of Stardust is not only about how it began, but about how it has been kept safe. Atoms that once lay in the hearts of old stars now call each other into cells, into memories, into dreams. To keep those dreams from being blown out by great winds, the universe arranged a marvelous system of guardianship. Tonight, as sleep comes light as mist, you can smile. Outside your window, the moon still crosses the sky. Deep below, the iron core still turns. Far away, gas giants continue their own slow dance. All of them, these quiet friends, are watching over your sleep and over life. Endosymbiosis, the journey of mitochondria and chloroplasts, when one cell welcomed another to live inside, and from there lit the energy for every idea of complexity. If you are lying still now, listening to your gentle breathing, imagine a slow-motion scene of the universe, where things do not happen with loud explosions, but as a very soft whisper. In that whisper, there is a meeting that lasted hundreds of millions of years between tiny, delicate beings, like droplets of dew. Bacteria, on one side, masters of respiration bacteria that knew how to use oxygen to release energy from food. A refined technique built on streams of protons, flowing like a light breeze across cell membranes. On the other side, primitive cells, not yet with a true nucleus, but beginning to experiment with wrapping up their genetic material, wanting to go farther, wanting more than a life of mere duplication and division. Then, in a moment nobody dated, out there in the primordial ocean, one cell engulfed and kept a particularly skilled, oxygen-breathing bacterium, and instead of digesting it, gave it water, shelter, and said, "Stay." In the soft dim of night, let your imagination drift closer. That tiny lodger slowly became the mitochondrion, the power plant of nearly all complex cells today. Mitochondria do more than burn fuel. They fuse the fates of two beings into one. The surplus energy they provide is like suddenly plugging a dim oil lamp into a city power grid. Every corner of the room brightens. Intricate tasks become possible. Before that, simple cells lived on modest reaction chains. Whenever they wanted to, build an extra room, say a machine to read and repair genes, or an internal transport system, they hit the wall of an energy bill too high. When mitochondria moved in, that bill was paid regularly by a warm flow of ATP, like a steady kitchen fire, opening the door for bold plans, forming a membrane-bound nucleus, deploying an endoplasmic reticulum network, installing microtubule transport, experimenting with new reproductive mechanisms, playing with longer lifespans and deeper molecular memory. Perhaps you're smiling now, thinking of a multi-generational family sharing a warm house. Endosymbiosis is just that. A co-living contract where benefits intertwine until they cannot be separated, in exchange for lodging and protection from outside turmoil. The bacterium, now mitochondrion, supplies the host with ATP, the energy coins. In return, the host cell provides food, a stable environment, and repair tools when mitochondrial machinery falters. The two gradually synchronize their language. Many mitochondrial genes are transferred back to the host nucleus, as if the master craftsman's secret recipes were locked in the household's shared safe. Why do that? Because the nucleus is safer, with more sophisticated repair systems. The most critical instructions are stored there, and parts are manufactured as needed. Mitochondria keep a small set of their own genes, a tiny scroll in their ancestors' handwriting, enough to coordinate urgent local jobs on site, because some decisions must be made right in the workshop, not by sending forms up to City Hall in the nucleus and waiting. We won't rush. We'll slow down. Like a friend sitting on a quiet American porch, looking out over dewy grass. Let's gently touch on a small detail that once stirred debate and is now broadly accepted. Mitochondria and chloroplasts each have two membranes. The outer membrane resembles the host's. The inner recalls their bacterial ancestors. It's a gentle trace, like dark rings in an old tree. Each season leaves a line. Then there's their tiny circular DNA, unlike the long linear strands in the nucleus. Add to that their way of dividing on their own schedule, not always synchronized with the cell's division like independent breaths within a shared piece of music. All are notes of evidence softly singing. We were once two, now we are one. As oxygen grew more abundant in oceans and sky, as we heard in the earlier part, where oxygen knocked at the water's surface, allying with a skilled breather became a golden advantage. Oxygen is both a life giver and a double-edged knife, easily spawning reactive molecules that can slice fragile structures. Mitochondria are like seasoned craftsmen, knowing how to use oxygen with the right force, at the right time, building enzyme walls to keep reactions from going wild. With them, the host cell not only harnessed oxygen's power, but also learned to coexist safely with a newly radiant world. And with abundant energy, the cell's imagination bloomed. It began assembling tiny organelles, peroxisomes to detoxify, lysosomes to digest, Golgi apparatus to package internal mail. A city had been sparked, but tonight's story has a second thread, soft as a patch of moonlight on a pillow. Chloroplasts. If mitochondria are nightside plants using existing food to make energy, chloroplasts are light factories, born when ancient photosynthetic bacteria found shelter inside ancestral plant cells, creating a miracle, turning light into sugar, pulling carbon from the air into leaves, stems, seeds. Once again, the pattern is uncannily similar. A cell engulfs but does not digest. A lodger moves in, bringing photosynthetic arts, two membranes, circular DNA, lingering bacterial enzyme patterns. Thanks to chloroplasts, Earth became a vast charity of sunlight. Solar energy packaged into sweet fruit, starchy seeds, sturdy wood. Plant life spread its arms, cooling the atmosphere, releasing oxygen to fuel respiration, and building green stages for all later stories, including ours. There's a charming detail rarely told in short tales. Endosymbiosis is not just a lucky one-time idea. It is a mode of evolutionary language, the language of cooperation. On the smallest scale, bacteria exchange genes horizontally, like good neighbors swapping seeds over a fence. On a larger scale, one organism accepts another into its private interior. Cooperation requires trust. But here trust is written in chemistry. Regulatory signals, feedback loops, switches that let the lodger work just enough, without overrunning, without turning into a usurper. Over time, genes shift toward the central control, the nucleus. Like family businesses merging their accounts, entrusting a single accountant, the house runs smoother, fewer quarrels, more synergy. Now, let's lean back further and open another door. Why did the complexity of animals, fungi, and plants need mitochondria so much? Answered in the voice of an old American mechanic: because of horsepower. To sustain a brain with tens of billions of neurons, to grow fine muscle control, and to operate multi-layered gene regulation, a cell must spend energy like a small town spends electricity. Mitochondria share that burden by distributing their plants throughout the cell, right beside high-demand sites, delivering energy directly and instantly. That image is tender. Tiny inner lights flickering like fireflies over a summer marsh, each a diligent mitochondrion, blinking in time with the tasks at hand. And there is a subtle gentleness too. Mitochondria do more than power. They help decide when a cell should live or die. When damage is too great, a cell must withdraw gracefully, rather than become a threat to the whole body. A sad yet wise decision. Mitochondria help send that signal, triggering natural programmed cell death, so the rest may thrive. In the dim light of your room, that act is like turning off a flickering bulb to protect the house's wiring, a quiet patience full of care. Another small and well-loved detail. Human mitochondrial DNA is mostly inherited from the mother. In each of us, mitochondria are like little boats that sailed from our mother's egg into the embryo, into our lives, carrying a faint resonance of mothers long past. At the population scale, scientists have traced those lines to map ancient migrations, like hearing old lullabies echo through centuries. For a sleep story channel like Smart Sleep, the image is tender. You lying there listening to a story of your mother's mother's mother. Energy lines quietly stitching time's thread, quilting you into humanity's great blanket. Back to chloroplasts. They have their own quiet songs, in dense green algal blooms, in new leaves opening to the morning sun. Each chloroplast is a loom of light. They align chlorophyll molecules into delicate ridges to capture light, then use electron transport chains to package energy into sugars. When you sip tea, when you touch the wooden handle of your toothbrush, when you rest your head on a cotton pillow, you touch energy threads that once passed through chloroplast hands. Through endosymbiosis, plants became the universe's contractors, receiving raw sunlight and delivering finished goods to ecosystems. In the quiet night, imagine a distant forest where light factories run the night shift under the moon. You can almost hear the faint humming of photosynthesis. Some may ask, but surely this wasn't the only story. Might there have been other symbioses, other failed trials? We are allowed to dream before we have proof. The microbial world is a ceaseless testing ground. There may have been endosymbioses that failed, marriages that did not last. What we know is that at least two great unions with the ancestors of mitochondria and chloroplasts succeeded so spectacularly that they changed Earth's fate. From them, life could write longer sentences, richer rhythms. We hear crescendos, evolutionary explosions, and long-held notes, quiet epochs. Through it all, endosymbiosis is a persistent motif. To grow strong by cooperating, to endure by sharing. And there is another tiny, often overlooked corner. The double membranes of mitochondria contain a signature molecule called cardiolipin, a special mortar found in bacterial and mitochondrial factories. It helps anchor proton-pumping turbines, those spinning enzyme complexes that make ATP so they can work smoothly. The chemical name may sound dry, but you can hear it as a slow song, cardiolipin, reminding us that structural artistry lies hidden in each effortless breath. Each time you inhale, billions of such turbines spin a tiny arc, noiselessly, just enough to feed the subtle current that lets your memory close its eyes in peace. Another softer question. Why did endosymbiosis, this elegant idea, arise when it did, and not earlier? Perhaps because oxygen had to reach a high enough level for aerobic respiration to truly pay off. Perhaps because host cells had to learn the etiquette of management, from eating, digesting, excreting, to keeping, protecting, nurturing. Evolution, like human life, needs time to learn gentleness. Once all sides were ready, a nod happened. From then on, our shared ancestors, affectionately called Leka, the last eukaryotic common ancestor, carried a full set of functioning mitochondria and a suite of complex cellular tools. Picture Leka as a warm grandmother with a heavy key ring. Each key opens a room: the nucleus, transcription machinery, cytoskeleton, and one special key for the mitochondrial engine room, where you hear a gentle hum of warmth. As with any lasting relationship, endosymbiosis is not free of conflict. Sometimes mitochondrial DNA mutates, machines misfire, or mitochondrial numbers go off balance. The host cell has maintenance crews, signaling pathways and watchful proteins to detect, repair, or remove faulty mitochondria. Some human diseases stem from such glitches. That is the cost of living in a complex city. More equipment, more risks, but overall, cooperation wins. For billions of years, most of us wake each morning, open our eyes thanks to energy from mitochondria, and eat lunches powered by sunlight, wrapped by chloroplasts in leaves. By now, if your eyelids feel heavy, we'll lower the story's voice further. Imagine walking into a quiet museum that displays only warm things: a small hearth, a wooden porch roof, a porcelain cup still faintly warm. Endosymbiosis is the coziest room there. It tells us that in a vast universe, life is strongest when it learns to live together. One cell opened its door to another, learned to let the stranger become family, and from that shared home, small descendants went out to grow forests, scatter flowers, write music, paint, and one day lay a hand on their chest and whisper, "We are indeed made of stardust, but we grew up by living together." And right now, in your body, trillions of mitochondria are busy, yet utterly quiet. They've done the same work since before humans had writing, lifting a thought, carrying a memory, keeping a heartbeat warm when the air turns cold. Outside, in the leaves of roadside maples, chloroplasts keep the day's song, gently catching sunlight and distilling it into sugars so that at night they can give the world a sweet breath. Listen just a little more, and you may hear the faintest whisper of this long cohabitation, a cosmic lullaby written from atoms born in distant stars. In the sleep that is coming, if you happen to dream of soft yellow lights from tiny factories inside you, or a green glassy canopy leaning over your window, smile, because that dream is not just a fantasy. It is the deep memory of life itself, the memory of the day. One cell opened its door to another, and together they became something wondrous. Tomorrow morning, If someone asks why we can think, love, sing, you can answer very slowly, because we learned to live together ever since we were stardust. Then to it, my dear friend, tonight, as you lie in a quiet room, the familiar sounds outside suddenly feel more distant. The soft hum of the air conditioner, the thinning traffic on a small street, the wind brushing the eaves, everything seems to settle, to make space for the oldest question humanity has carried. On the long journey from stardust to life, has anyone else walked this path before us? In the gentle darkness of an American night, it's easy to feel small, but that smallness does not make us alone. On the contrary, it's like a child standing before the vast sea, not afraid, but eager. The universe is still whispering something to us. Sometimes, we are simply not quiet enough to hear. Try taking one step back in your mind, as if standing at the edge of the galaxy, looking down at Earth. A pale blue dot, floating in endless black. Around it, hundreds of billions of stars, like hanging candles. Every star may have planets. Some fraction of those planets may have liquid water. Some fraction of those may have stable atmospheres. And some fraction of those may have life. Seen that way, the idea that only Earth holds life starts to feel strange. Almost too strange, as if we found a single wet grain of sand on a beach thousands of miles long and concluded the sea touches only there. Dear listener, you have lived through many seasons, many years. Perhaps you have looked up at winter skies in Iowa, summer nights in Texas, foggy evenings in New England. Has there ever been a moment, among the glittering stars, when you felt as if someone or something might be looking back, not with eyes, not with words, but with the quiet presence of those distant points of light? Modern science has begun to hear those whispers more clearly. Telescopes like Kepler, TESS, and others have discovered thousands of exoplanets, worlds orbiting their own suns. Some are close to Earth in size. Some lie in the habitable zone, where water need not freeze nor boil away entirely. Some show hints of clouds, oceans, and atmospheres. Imagine, somewhere tens of light years away, a planet circling a gentle star, whose light is a little redder than our Sunday. On that planet, the shores might be tinted purple by unusual minerals. In its sea, there may be self-replicating molecules trembling under their first dawn, or life may be further along, creatures with glass-clear eyes swimming among glowing coral forests, or on land, plants with deep green leaves shaded with indigo, drinking in red-orange light from their star. We do not know, but the universe does not forbid it. Strangely enough, everything that would make life there if it exists also starts with stardust. With the same types of atoms: carbon, hydrogen, oxygen, nitrogen, blown out by ancient supernovae, perhaps by the same one that gave birth to our Sunday, or by another far across the galaxy, birthing a completely different system. If so, then life anywhere is distantly kin to us, not in form or mind, but in substance, as if the universe had its own shared DNA written in how electrons jump between shells, how carbon bonds into long chains, how water forms hydrogen bonds. The universe knows how to make life, and it is unlikely to do it only once. Tonight, I'd like to invite you to rest in that thought, not as a declaration, but as a lullaby of possibility. Perhaps life is blooming on planets we've never seen. Perhaps some civilizations went dark millions of years ago, leaving signals adrift, like whispers from those long gone. Perhaps some minds are looking up at their own skies, asking the same thing: Are we alone? And perhaps, just perhaps, across hundreds of light years, those thoughts accidentally fall into sync, a miraculous moment that no one notices. We listen to the universe in many ways, with giant radio telescopes pointed at the sky, with sensitive antennas searching for anomalies in signals, with optical telescopes watching stars' light wobble, with probes like Voyager carrying greetings in 55 languages, drifting toward distant stars. But sometimes, no matter how strong our tools, what we lack is not equipment, but perspective. Maybe life doesn't have to use water. Maybe intelligence doesn't have to be carbon-based. Maybe their signals aren't radio waves, but patterns of light, gravity, or something we haven't conceived of. The universe is under no obligation to communicate in the formats familiar to us. We're only just beginning to learn. Imagine someone living in a small house in Montana, listening to the wind in the pines. Even if they don't see their neighbor miles away, they know someone is there. From a light on the horizon, a far-off dog's bark, fresh tracks in the snow, the universe is similar, but its traces are subtler, demanding more patience. You know, when humans first saw the pale blue dot photo, a tiny blue speck captured from 6 billion kilometers away, many cried, not from loneliness, but from recognizing life's fragile beauty. And from that dot, the question of other blue dots became impossible to ignore. If Earth is not unique, if there are civilizations millions of years older than ours, if there are eyes not human looking at their sky and wondering, then this night the one you're spending listening to me is not empty. It's a velvet curtain behind which countless other stories could be unfolding. We do not know whether anyone is out there, but not knowing does not mean they do not exist. Silence is not denial, it is an invitation. Let me tell you one more thing before you drift off. Not because it's some grand secret, but because it is gentle. When scientists send signals into space, they know very well that no one may answer. Yet they send them anyway, because that act is not only about searching, it is our way of saying to the universe, we are here, we are alive, we are curious, we hope. Cisristani. And if life exists elsewhere, they may be doing the same, not necessarily to find us, but to send their greeting. A greeting lost in the sea of night, a greeting that we might recognize only if we learn to listen the right way. In the end, the question, are we alone, may never demand an absolute answer. Instead, it invites us to open our hearts to the possibility that life is not a fluke, not a mistake of the cosmos, but a habit, something stars do when they grow old. They make elements. From elements come molecules. From molecules come cells. Cells talk in chemicals. Then come beings that feel. Then beings that love, remember, dream. If that process happened naturally once, it can happen many times. The night sky is not mere darkness. It is a library of unread stories, a map of unopened possibilities, a doorway slightly ajar to worlds unknown. You are not alone on this night, not only because I am here telling you this story, but because behind every star you see out your window, there may be other pairs of eyes looking toward us, not to watch, but to wonder, to hope, to ask the very question you are asking now. And until we know for sure, until the universe whispers clearly enough, we will keep listening with telescopes, with probes, and with hearts that always want to know a bit more. The night has grown deep. Close your eyes now. Let the question, are we alone, drift away like a boat loosening its moorings on a still lake. Because sometimes It is the question, not the answer, that makes us feel present in this vast universe. And if there is someone out there, also made of stardust like you, who knows, they may be wondering the same thing at this moment. Under another sky, you can close your eyes now. Let your thoughts dissolve like mist. If your mind still wants to wander, let it keep going into the next video, where we journey deeper into the mysteries of the soul. But if your body is tired, just let this sound lull you to sleep. No need to try, just breathe. And remember, everything you're searching for is already resting quietly within yourself.